So today is all about correlation coefficient. It is the symbol or the notation for it is a lowercase r. So the correlation coefficient r, that's what goes in that little blank, measures the strength and direction of linear relationships. So that's the first thing that we have to pay careful attention to, is that correlation coefficient, or R, only applies to linear relationships. So last time we talked about a couple of different forms. It can be curved, it can have groups or clusters, it could just be nonlinear, or it can be linear. Today, it has to be linear. Your scatter plot has to follow some kind of a linear form. So R, the value of R, tells us how close to a straight line the data points appear. R must be a number between -1 and +1. And then down below, you get a picture of some different R values. And I just want to take a moment for you guys to investigate and see if you can make some connection between the picture and the R value. So we know that this is perfect, a perfect linear. This is strong, weak, none, weak, strong, perfect. So see if you can look at those R values and make some conclusions or some assumptions. Give you like 30-ish seconds, really think about it. About 10. Is there anything that's standing out to you guys? Yeah, thank you, Carter. So he's saying the closer that you get, or the higher that you get in your number, or closer to 1, the stronger your relationship becomes. So a perfectly linear relationship has an R of 1. That means that the slope of this line is 1. So perfect relationship 1. 0.93 is still a really strong relationship. Once we start getting down to about 0.5, it's now entering the weak zone. Notice no relationship would be a 0. None would be 0, and then it works its way back up. There's one other thing that we can notice from this. Do you guys know what it is? Aaron?
Whether it's negative or positive,
Perfect. So up here in the box, we have that this R is going to tell us strength and direction. Remember, direction is it positive or is it negative? So here you can see that all of the positive relationships or associations are positive valued, and all of the negative relationships are negative valued. So that is the strength and the direction. The sign tells you direction, the number tells you strength. Thank you guys for helping with that. Hannah?
So mostly just like talk myself through it. So you could say like from 0.01 to 0.49, you would consider that a weak, and from like 0.50 to 0.93, a strong, like that's how you would say that?
Yeah, so we think your brain's going in the same direction as my brain, because if you hop down just a little bit, in this box, I'm going to give you all of those ways that you would label it. If that doesn't answer what you're talking about, tell me again, okay? Okay, so now that we've made some of those connections, we can say a linear relationship is strong if points are close to a linear pattern, which we already knew, but now we know that this value of R is approaching 1 or -1. The closer you get to 1 or -1, the stronger the relationship is. Then over here, I'm going to give you the words to describe that strength. And I tried to, the reason these scatter plots are here is to just help you make the connection that if the R value is negative, you are looking at this kind of relationship, it's going down. Remember, you can always draw that line in. And if it's positive, then your association is also positive. But this box now is going to give us the words that we can use to describe these. So if it's -0.8 to -1, you have a strong relationship, which means on the other end of that, it is also strong. The sign doesn't affect your strength, it affects your direction. Then from about half to 0.79, you're in the moderately strong category. And then and really 0, you guys know if it were 0, it'd be no association. So really anything about 0.49 or less is going to be weak. I've never really seen in any of the lessons I've done or stats classes that I've taked, that's good. I've never seen a correlation of 0. I've never calculated an R value of 0. But in theory, R of 0 would be no association. Does that help, Hannah? Was that what you were getting at? Okay. And then last up, in using R as a description, I'm going to help you think of a way to estimate. So to estimate the correlation coefficient, imagine drawing an oval, or even a rectangle would work, it doesn't matter what shape you use, around the points. So if I drew an oval around the first one, and then the third one, I'm skipping the middle one on purpose for now. The bigger your shape gets, the weaker the relationship is. So the rounder the oval, the closer the correlation will be to 0, and the longer or skinnier, the closer it'll be to 1. And then, like I said, you could use a rectangle too. Doesn't matter what shape you use. So I would say that this one is strong. This one, I think he might be moderately strong. And this one in the middle looks very, very similar, except for what? There's one thing that's different. It has an outlier. It's got this little guy hanging out up here. So as much as we'd really like to just ignore him and just draw an oval around the points that should go together, which would be weak, even without that outlier, this relationship in the middle would be weak. Like his oval is bigger than the rest of the ovals. But if we had to include that outlier, it'd be even weaker. So it's already weak, but if you had to include that one guy hanging out on the edge, it becomes even weaker. Which means you're going from an R value, which we can see up above is 0.93. Like if these two look similar, would you guys agree? This graph and this graph? Do you think those are pretty close?
Yeah.
Anyone? Yeah? So maybe he's like a 8.5. Maybe this guy's like an 8.5. Maybe he's a 9. Maybe he's a 9. I'll walk on the wild side and say 9. This guy might be like a 70. Or maybe I should bump him up. No, I think 70 is good. But this guy, holy moly. Without the outlier, he might be around 50, but with the outlier, he's not looking good. I maybe put him at 4.9. Now, is this a perfect science? No. A lot of the time, you have the R value. You're not just sitting around estimating these values, because that's almost as bad as the last time we were discussing it. But they want you to be able to start eyeballing, oh, these should all be negative. Brinley, is that what you were going to tell me?
Yeah.
Good looking out. So if you have something slightly different than me, that's totally fine. Because like I was saying, we're just, on these ones, just eyeballing it. So now, on this side, they want you guys to come up with the R values, and then I'll give you the actual R values. So use pencil for sure. I'll leave this side up for you, frozen on my screen, so that you don't have to flip back or forth if you don't want to. And you can use the one that they have, or I have labeled with the actual R as your guide. Don't use our ones at the bottom. Totally okay if you're wrong, just make a guess. Oh, some of you guys are drawing ovals. So smart. Good. Let's go at least 30 more seconds. We're going to use your calculator next if you're just done and waiting, just as a heads up. About 15. Okay, so the top left, these are the actual calculated R values. Top left is R is 0. Or your book labels that as 0. He looks kind of negative to me though, right? Yeah, negative. I think I agree with Carter. Your book says 0, but I think it looks negative. Did anybody draw positive on? Yeah, it definitely doesn't look positive. Okay, next one they have labeled as R is negative 0.3. Probably because of these guys here ruining it. Top right, they have at 0.5. Bottom left, they have R is negative 0.7. Bottom middle, R is 0.9. The last one they have as negative 0.99. I think I want to write all of mine like money. That makes me feel better about it. So I usually like to write my decimals as money and think about them as like 30 cents, 50 cents, 70 cents. How'd you guys do? Were you kind of close? Ooh, good. Good job. If you didn't get any of them, don't feel bad, because it took me at least a full school year before I felt good about estimating accurately. Okay, so the bottom part, I gave you 2 tables because I'm going to show you how to calculate R using your calculator. So any list you want, let's enter in this data, and I tried to use shorter data sets so it wouldn't take us 10 years. So I'm just going to go into Stat, Edit, and then I'll put mine in list 4 and 5. Remember to clear out your list, highlight the number, hit clear, not delete, don't hit delete, clear, enter. Oh, drat. Then you want to always make sure that when you're done, your lists end at the same point. Is 20 seconds enough? About 10? Three. Okay, we're going to Stat, Calc, so arrow over to Calc, and you want to choose linear regression, but you don't want 5, you want 8. So you want to go to option 8. Mine was in list 4, and you have to hit blue button and the number of your list. You can't just type in L4. Your calculator won't read that right. So I think mine was in list 4 and 5. Enter, 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 and then one more enter. Your R value is the bottom value. So our R value is 0.95. So that one's really strong. So I'm going to write down those buttons. It was stat, calc, 8. That gave us an R value of 0.95. So now I would like for you to do it one more time on this data. I don't think you need this list anymore, so you can use the same lists or you can use new lists. It's up to you. So you guys calculate the correlation between the Maine divorces in Maine, and butter consumed. Do you know what you're doing? Thank you. Yes, babe.
Go to mode. And you need to turn your stat diagnostics on. So go to mode. Arrow all the way down. And you'll get an option that says stats diagnostics. You need to turn it on. Did you get it? Okay.
About 30. $10. Okay, what'd you guys get for this R value? What? So let's think about that. We have this scatter plot that is relating the amount of butter people eat in Maine in relation to how many divorces there are in Maine. And it's almost a perfect correlation. Do you think that the amount of butter eaten predicts the divorces? Probably not. Do you think I mean, maybe they're eating so much butter and like gaining a lot of weight, and then they're like, well, I just can't anymore. Because now you're 500 pounds. When I met you, you were 100 pounds. Maybe? Probably not though, right? So, because of this, we have to talk about some properties of correlation, because obviously we need a little bit more information if we're getting a relationship between margarine and divorce rate. So that's where this paper comes in. We're going to talk about some properties of correlation, and we will revisit those two examples in just a moment. So the first one is correlation makes no distinction between the explanatory and response variable. So, actually, I don't want to highlight that part. It only measures how strong the data is. So switching the axes does not change R. That's the one thing that I wanted to highlight, and then I'll give you more detail on what they're actually telling you. So this first graph is a graph showing you the relationship between sprint time and long jump distance. So they want to know, is there a relationship with our sprint time and the amount or the distance our athletes can jump? And what you see here is they're using sprint time to predict. We have a negative relationship, and this R value is R equals negative 0., let me make sure I have the right value, 869. So if we plugged in those points, if we put in the data, and I do have the data in your notes, so we could do this, our calculators would give us negative 0.869. Now this is the same exact data, but I switched the axes. So I put long jump on the X. I want to see if long jump will predict sprint time or explain sprint time. The R value did not change because the relationship didn't change. Switching the axes does not change the relationship. It just changes the way the scatter plot looks. Are you okay on that one? Number 2, R has no unit of measurement. So we don't say R is negative 0.869 seconds. It doesn't have a unit of measurement. R does not change if the units or unit of measurement changes. So R doesn't change even if your unit of measurement changes. So let's be more specific on this guy now. Once again, we have our original graph of sprint time and long jump distance, but to fit these in, I had to make them really small. So I have to highlight for you that the left-hand one is in inches. If you look at the y-axis, it's in inches. And we know that R is negative 0.869. So last night, I went in, literally, I'll show you my notebook. This is my notebook from last year. I went in and changed all of those inches to centimeters and graphed it again. And that's what you're seeing on this graph. So this one says inches, this one says centimeters. The scatter plot looks exactly the same. The only thing that's different is notice the scale on your y-axis is different. The numbers are different, but the relationship doesn't change. So R has no units of measurement, which means if you convert from seconds to minutes and inches to feet, your R value does not change. And then the next one is the one that has to do with the butter example and the reason why your testing example is back. So R does not imply or equal causation. R does not imply or equal causation. I don't want that color. I don't know what color I want. So let's talk about what that means. So I went back and reviewed this example because when I talked about it with you guys, I couldn't remember why they went from income to low attendance. So what was happening in this example was lots of school districts know about the achievement gap and know that their low income students typically score lower than their middle high income students. But can they control their community's income? No. So they thought, well, what's another thing? What's another commonality between those students besides just low attendance? Low income. And they come up with low attendance. Maybe these guys are low attenders because they don't have as much support at home, or maybe they're helping to support the family by working. So they say, okay, well, we can't control income, but we can control attendance. So let's see if there's a relationship between attendance. And we do have a relationship between attendance. So here was their thinking. They think, okay, low attendance causes low score. So they spent, this is just that last page they were on, they, and by they I mean school districts, and this is a real example, I just didn't pull the exact source. They spend all this money to create programs to increase the attendance at their schools. And what they found was high attendance still low scores. So they get this scatter plot and they're like, there's definitely a relationship. So it's got to be the attendance. And what we're seeing here is there is a relationship, but it does not cause the low scores. Does that make sense? You're sure? Okay. What is happening here is called a lurking variable. And we talk about this a lot in the next unit. What is happening here is called a lurking variable, which means there is some other thing happening here that is causing the low scores. So maybe it's not the low attendance that's causing the low scores, but one of those other things I mentioned, like what if they work to help support the family, and those stressors and everything that comes with that is what is causing the low scores. So lurking variable means there's something else behind the scenes that we haven't considered yet that might be related to all this. Does that make a little bit of sense? Okay. And then this guy is first, this is not causation. So the butter example is not causation, and it's not a lurking variable. It's just coincidence. So we got to be on the lookout for those things. There are a lot of weird, bizarre things that are very highly correlated that are just coincidence. And in this case, the main divorces and the butter consumption is one. So this, there's probably a reason, and it's a lurking variable. This one, just coincidence. Okay, correlation is not resistant to outliers. Correlation is not resistant to outliers, which we already know because we were talking about on this page how this is already weak if we don't include the outlier, but then when we include it, it's even less strong of a relationship. So outliers in the pattern strengthen R, and outliers outside the pattern weaken R. Oh man, my pictures are in the wrong order. So this first scatter plot is the original scatter plot, and he has an R value of 0.41. Very weak relationship. Now, if I add an outlier that is in the pattern, so this is an example of an outlier in the pattern. The R value goes from weak, 0.41, to 0.94. By adding this one outlier all the way out here, you take a weak association and all of a sudden it turns into a very strong association. The opposite, though, happens here. So that outlier is outside the pattern. So far away from this line. This was in the line, far away from line. Your R goes from, remember this is the original, 0.41 to 0.11. And then lastly, correlation is not a complete summary of the data. And this last scatter plot is an example of that. So here's what I want you to notice. If we ran correlation on this, we would get a line something like this. But is anybody noticing these three groups? If you separate out those three groups, what kind of relationship do they have? So this is positive. What about these guys? Negative. So in this case, we would get a correlation, but what's probably more interesting about this data is these three groups. So if all we reported was the R value of this data, we would not see groups or clusters. We would not see any groups or clusters or any interesting things. It won't tell us if the data's curved. Even if it's curved, we could get an R value. Should we? No, because remember, correlation is only linear relationships. So if you know that the graph is curved, you would never find R. But if you just got a table and they said find R, you might run into some trouble if you didn't know that the graph was curved. So these are our properties of correlation. Now the last problem, I think that I'll make a short video. So between now and when you watch it, enter that data into your calculator. And then this will go really quick because it's just fill in the blanks. Yes? And you'll look at your, can you do? Okay.